So, semi-definite systems or degenerate systems are systems that aren't connected to ground. Okay, there's a system where no inertial element or spring is connected to ground. Okay. Now, an example of a semi-definite system could be the turbine compressor and obviously the shaft connecting the two in a jet engine. They're not connected to ground. Okay, they are connected to each other. Obviously, the turbine turns the compressor in a jet engine, and that shaft will have a certain element of torsional stiffness. Okay, and so this could be the inertia of the compressor. You've got your shaft, and this could be the inertia of the turbine. They're not connected to ground in any way. Okay, they're connected by bearings. Okay, but obviously you've got a system that there is semi-definite. But this system could be sort of floating in space. Okay, it's the same sort of thing, not connected to ground. And to solve it, you go through the same process. Okay, so again, our diagonals will be the certain masses, and here there's only one spring in the system. It's connecting the masses together, and so we've got K and K in the diagonal, and we've got minus K and minus K in the off diagonal. Okay. Again, you can make the substitution for x1 and x2, and you can go through and find our system here. This is the mechanical impedance matrix. We can find the determinant, and we get our natural frequencies. Okay, and so if we do that, you can see quite clearly that we end up with omega squared outside of the bracket with a quadratic inside it. Okay, essentially. The only way this solution works is if this is 0. Okay, so there's one solution, omega 1 squared is 0. Or if this lot is 0, so you get a second value for omega as well. 2 degrees of freedom, 2 natural frequencies, but one of those natural frequencies is 0. Okay, and that makes sense. If the system's floating in space, the two masses are just moving around together. They're not oscillating at all. Okay, there's no frequency because it's not oscillating. The other one is going to be a relationship between the masses and the stiffnesses, okay, where the masses are moving around. The thing could be moving around in space as well, but those masses are oscillating together this frequency, dependent upon these masses. Okay. It's quite clear that if mass 2 was huge and mass 1 was not very huge, okay, what you end up with here is you end up with this number being insignificant compared to this one, so you end up with km squared, m2, over m1, m2. The m2's cancel, you end up with k upon m, which makes sense. Mass 2 is ginormous, okay, mass 1 is just oscillating against mass 2. It's like a single degree of freedom system, okay, so that's worth remembering. And so we substitute those values of omega back into the mechanical impedance matrix to determine the mode shapes, and we end up with 2 mode shapes. The first mode shape, we said, is no oscillation. And so obviously if mass 1 moves by 1, mass 2 is going to move up by 1. Okay, so you end up with 1, 1 as the first mode shape. And for the second mode shape, so there's 1, 1, okay. That's called the 0th mode. The second mode shape, omega 1, okay, is obviously a relationship. It's going to end up being a relationship between the masses. Okay. And again, if m2 is ginormous compared to m1, this term drops to 0, and so you end up with basically mass 1 moves up by 1, m2 is not going to move at all. Okay, which makes sense. It's a single degree of freedom system. So in this case, the motion of the masses is relative to each other is dependent upon their masses. Okay, it's not a certain value minus 1 or plus 1 or whatever. It's dependent upon the masses. So if the masses are equal to each other, it's going to be minus 1. If they're not equal to each other, it will be dependent upon those masses.